So in the last class, we had discussed about. Now in this case, first we started using an NMOS transistor. Okay, so NMOS transistor was being used, and we found that the gain was expressed as something like minus GM1 by GM2 with some eta factor, and this eta factor was a kind of problem for us just because it introduces a nonlinearity, right? So this was introducing some sort of nonlinearity into the gain expression, and we just want to eliminate this issue. So what we did after this, so how would we eliminate this nonlinearity problem that comes just because of this eta factor? Yeah, how did we remove that body effect? Yeah, so rather than using an NMOS, what we did is that we just switched this NMOS to a PMOS device. So due to which we have eliminated this nonlinearity error because of this eta factor. But apart from this, we also had some other issues, right? So the very first issue was about the output swing. Okay. Now, when I compare this output swing with respect to a resistive load, what was the VO max and VO minimum for our diode connected load? Yeah, so in this case, our VO max was reduced by a quantity of VDH. In the case of PMOS, then I need to put a modulus. So this is how the VO max has been reduced. Whereas in the case of VO minimum, it was at VO V1, right? So this one, when I compare with a resistive load, what has happened is that in the case of a resistive load, we had our VO max to be equal to VDD. But right now, this VO max has got reduced by a threshold value. And if you are working with a VDD or power supply which is around 3 volt, and if you have this VDH which is around 0.7 volt, what happens is that you have already reduced more than 20% of your supply in this reduction itself. Am I right? So this becomes a very huge problem when we go for a lower technology where our supply is reduced to 3 or lesser than 3 volt. Okay, so that becomes a kind of issue for us. And apart from this, we also found one more thing. What was the second issue that I can state here? So the gain expression was re-returned, right? So we used something like W by L factors. So when I used a W by L factor, the gain was constant, but the whole problem is with respect to the disproportionality, right? So this was leading us for a disproportional sizing, and this disproportional sizing had some sort of bandwidth issue. Okay, so this was our problem that we had when I went for VOE1 equals to VOE2. Okay, so we had disproportion in the W by L factor of both PMOS and NMOS, or between the load and the input device, and the input device has become too much bulky, and that leads to some sort of reduction in the bandwidth of the circuit. Okay, so that is what we had. The other way to work around for the gain is to work with the VOE factors. So I can have my VOV2 to be much larger than VOV1 in order to have a gain. But in that case, what we ended up, the Q point, yeah. So the output Q point had some issue, right? So I think in the video I have wrongly spelled as the Q point is shifting towards the top, but actually it is getting shifted towards the lower half of your region. Okay, so basically there is a shift in the Q point, and that actually disturbs my output swing. Okay, so these are the two major issues. And now what we do is that I just want to show one exercise problem. So you can just make a note of this exercise problem and work for that thing. Just make a note of this problem. We will not do it right now just because we are too much lagging when compared to the other 2 sections or the 3 sections. Okay. So try to calculate, and then we'll have a discussion on this whenever time permits. So what is given here is the VOV. So from VOV we can actually compute the VGS value. So it's as simple as that. So once I have the DC quantity, then you can go for calculating the small signal gain. Clear? So now we have spoken about these disadvantages. So the major disadvantage is that my VO max has got reduced by a large quantity. Okay. Now let us try to address this with, and also the disproportionality, with something known as CS amplifier, or the common source amplifier with current source load. Okay. So generally this structure could be drawn as something like this, right? So we have a current source, and that would act as a kind of load for our input device M1. Right? So now how would I realize this current source? So how do I physically realize this kind of current source? So what am I supposed to do? Yeah, so I have to bring one of the MOSFET in the saturation regime, because in saturation regime the current is almost constant. Okay, so what type of MOSFET I have to choose? Can I use an NMOS transistor, or should I need to go for a PMOS transistor? NMOS? Okay, so let us go with the NMOS, but because the source terminal of the NMOS has to be lower than compared to the drain potential, right? So whatever the source potential that I have has to be smaller than compared to the drain potential for an NMOS. So if I do so, what happens is that whenever there is a swing at the output, what is happening across the VGS of this guy, M2 transistor? The VGS is varying, which means that the current is no more constant. I cannot use that. Okay, so then what type of MOSFET I can replace for this ISS? A PMOS? Let us try. So let us go with the PMOS. And in this case, we know that for PMOS, the source potential has to be higher than the drain potential, so I can flip it. And let me bias this with some constant voltage, something like VB. And now in this case, can act as a kind of current source? Yes, because the gate is fixed, the source is also fixed. So the VGS of this M2 is always fixed, due to which the current is always a constant, right? So for this, please don't use an NMOS. If at all, if your input device is an NMOS, make sure that your load is a PMOS. Clear? Yeah. So having done this, let us try to analyze the output swing. Okay. So I'm just rather than going for a small signal and then later looking into the output swing, we are going in a reverse way, where I will first talk about the output swing and then later I will talk about the small signal gain. Okay. Now, for the structure that I have at the bottom, that is for M1 transistor, we know that this relation of ID versus VDS, right? So we have a bunch of graphs. This is the line that I would get, or the current line that I would get for VGS that is less than VT, and after then for higher and higher values of VGS. Now what I have done really is that I have plotted the IV cara, or the output characteristic graph of this M1, and if at all I want to extract this output swing, I need something else, right? What else we need? Yeah, I need a DC load line. Basically I need a load line which has to be plotted on this graph in order to extract the output swing. But how will what is the type of graph that I can get out of this M2? Now, should I need to plot ID versus VGS, or I have to go for ID versus VDS? In the previous case, both our VGS and VDS was same, so there was no issue. But right now, in order to plot the load line of this M2, should I need to go for this plot or this plot? Yeah? ID versus? But can I relate this VGS with respect to Vout? Because the gate is fixed to a voltage VB, the source is also fixed to a voltage VDD, and that quantity will never meet my x-axis of this graph, right? Because in this case, my VDS of this M1 is basically talks about the Vout. Okay, so what I am plotting has to be plotted, the DC load line has to be plotted on the same graph, for which the x-axis of both the graphs have to match, otherwise I cannot plot it. So in that case, I cannot use this plot just because the VGS, the gate nor the source are connected to my Vout. But what happens is that when I look for this VDS, I can split this VDS2 as something like VD2 minus VS2. So again, when I look for this VD2, what is my VD2? The drain potential is connected to my Vout. So that is how I can use my ID versus VDS graph rather than ID versus VGS graph. Is that clear? Yeah. So now we got to know that I have to use this, but let us try to plot this figure and see whatever plot we have to get it. So I'm just using the first quadrant, so due to which I will write it as VSG2 and then ID2, and I'm just putting a modulus just to make sure that the PMOS currents are being plotted in the first quadrant. Clear? Now, how will I draw the graph of this? Now, what is my, sorry, nobody noted, VSG2, yeah. So, what is my VGS of my M2 transistor? It is being fixed to some sort of VB potential, right? So, it is something like what I have here is that I have a negative potential and then over the top I have some positive potential. So, it is something like this. So, plus and minus, okay? So, now whenever I have this fixed value of VGS for M2, will I be having some bunch of lines like this, or will there be only single line that I have to plot? It will be a single line, right? So when I try to plot the same, what happens is that I would get some sort of character where this value is nothing but my VSG, and that's supposed to be equal to my VB. Okay? Is that clear? Yeah. So now that I have got this, now I want to translate this graph onto this graph. So for which I have to first match my x-axis. So let us look for this x-axis. This x-axis, as I said before, it is split as VS2 minus VD2, and whereas here this would be equal to VDD minus Vout. Okay, but the axis that I have plotted for the M1 is basically just Vout. So what happens is that whatever the point that I have here has to be mapped onto this, right? So what I do is that is it okay that I'm just switching between these two graphs with not enough room between them? Okay. Yeah, so what we do is that let us try to take this particular point where my VSD2 is basically equal to 0. Okay. So now that I'm substituting that value over here in order to translate this entire quantity in terms of Vout. So when I do so, what I would get is that my Vout would be equal to VDD. So the 0 point is basically getting translated onto this x-axis at this particular point where my Vout is equal to VDD, because this is my Vout graph. Am I right? Yeah. So now that I've picked my 0 point and I've translated that 0 point onto this graph. So now let us pick this particular point where I'm at the edge of saturation. Now let us take it as VOV2. Okay, am I right? So what is my VOV2 here? Yeah, it is VB, VGS minus VT, right? Yeah. So it is nothing but VB minus VTP, modulus of VTP. Okay. So that particular point I want to translate onto this graph. So how will I translate this? So again, what you do is that you just substitute this value in the place of this expression, so that what I have here is that VOV2, and this VOV2, when it plugged here, it would translate as something like VDD minus VOV2. So now that what happens is that from the previous value of VDD, I have to shift towards the left because the Vout has got reduced. Okay, so that particular point would then, I'm just randomly picking. Okay, so it would be something like this, and after then the graph would be somewhere like this. Is that all clear? So this entire graph is being mirrored on to the top graph, which looks something like this. Okay, and this value is marked as VDD minus VOV2. Is that all clear? Yeah. So now we will look for the region of operation, and then later we'll try to evaluate the VO max and VO minimum from this graph, right? So what I can do is that let me choose this particular point where I could be able to see that the orange graph is intersecting with my green graph at a particular point, which is nothing but the edge of saturation of my which transistor? M1. Okay. So let me mark this edge of saturation as VOV1, okay, with respect to M1. So if I'm, let me choose, yeah. So if I'm within this zone, okay, what is my M1 and M2? And if I'm within this zone, in which region my M1 and M2 are operated in? So in this region, okay, so M1 is basically in linear, right? What about this M2 transistor which is being plotted in orange? Okay, M2 is in saturation. Can I use this region for picking our VO max or VO minimum? No, because for picking I have to make sure that both the transistors are in saturation. So I cannot use this segment at all. So all of these segments has to be removed. So let us go for the other extreme. So in this extreme, what is my M1 and M2 are? Which region my M1 and M2 are? Okay, so M1 is in saturation, but what about my M2? Yeah, it is in linear region. Okay, so are you clear with this? Right. Now it is only this particular region where I could able to see that both of my M1 and M2 are in the saturation. So then I have to use this region in order to read out my VO max and VO minimum. So in order to read out my VO max, I will pick this rightmost extreme region, and when I look, so what is my VO max that I can get out of this graphs? What is the segment, or what is this particular boundary line that separates this region from this region? Yeah, it is nothing but VDD minus VOE2. Am I right? So this is my VO max, and again, in order to read my VO minimum, I have to move towards this edge where I'm separating this region from this region. So what is my VO minimum here? It is VOE1 itself. Okay, so this would be my VO minimum. So if you people are not clear, then I can just draw one more plot where it becomes much clearer. So I have, so now the whole point is that I just want to draw a graph, but whenever we try to draw an output swing graph, we always talk about the base level. Am I right? Now, what is the base level of this output? Yeah, in the case, okay, so let me recollect whatever we have done till now. So for the case of an RD or a common source with a resistive load, the base point was just simply written as VDD minus capital ID times RD. That was defining my base level. So in the case of a common source amplifier, with what was the base level for this swing? It is VDD minus, yeah, VGS2 was the base level, and over that I had a swing. Even here over this level I had a swing. That is all different story. But in order to plot this, first of all I need to know what is the base value or the output Q point. Now the question is, what is my output Q point? Can you answer it? Yeah. Is it VDD minus VSD2? I don't think so, because I'm in the saturation region for the entire segment. You see, over this entire segment, I'm in the saturation region. Any value of VDS can fit over there, or VDS2 can fit over there. No, it is not VDD. Yeah. Okay, so I will not trouble you much. The point is that there is no proper defined DC Q point for a common source amplifier with a current source load. Okay. Now, how will I fix my Q point then? So this leads to an important topic which we call it as common mode feedback. Okay. We will not use it here, but I'm just giving this word so that whenever we talk about a differential amplifier, we'll discuss about this particular common mode feedback circuit in detail. But as of now, there is a kind of circuit that helps us to fix the output node to a particular value of DC. Is that all making sense? This common mode feedback is used to fix the output Q point, okay, only for current source loads. Okay, so please make sure that, because here nobody is there to control my output Q point. It can be any level. Okay, so we need an extra circuitry to deal with it. That extra circuitry is called as a common mode feedback, and that will help us to fix the output Q point to a desired value. Okay, say for example, I want this output Q point to be fixed at VDD by 2, we can do it. with that network. Does it make sense? No, you just see the region where I'm in saturation. This is my V out, the drain of this M1. So throughout this entire segment, I can be anywhere, right? The Q point can be anywhere here to here. It is not equal to VDD. If I'm equal to VDD, my M1, my M2 is in linear region. I cannot be there. I have to be within this region. But which particular point where I have to fix my Q point is the major question. Okay. So we always wanted the Q point to be somewhere in the middle of these two segments. Okay. So that particular point has to be fixed by an extra circuitry which is called as a common mode feedback. Is that clear? Yeah. So now that, let us assume that I have fixed my Q point. Okay, base value is fixed. Now what I do is that I will just try to create a small wiggle. Okay, I'm just leaving out the DC component. I'm just trying to work only with the small signal here. Now whenever there is a positive peak, from this base level, I will just be stepping down. Now till what extent the magnitude of this output negative swing can step down? So what is the minimum voltage that I need to maintain across this M1 such that I am in saturation? Right now my VDS is at the top, VDD by 2. My VGS minus VT is my VOV level, right? So what I'm trying to do is that the drain voltage is stepping down from the value of VDD by 2 and then it just keep reducing. So in this case, when I'm in this position, am I in saturation? Yes. When I'm in this position, I'm in saturation? Yes. Yes. What happens after this? I'm getting into linear. So what is the minimum value that I can have across this VDS? It has to be VOV1, right? So this value, the minimum value that I can have is equal to VOV1, and that is what we read at the beginning. In the graph that I've shown before, the VO minimum is nothing but is equal to my VOV1, okay? Similarly, what happens when I have a negative swing across my input such that it creates a positive swing at the output? So how far it can go up? So again, when I try to have a swing, what I'm trying to do is that I'm trying to reduce the value of VDS2. Now how far the VDS2 can be reduced for the M2 transistor? What is the minimum voltage of VDS2 I can have such that still I am in the saturation regime? It is equal to VOV. Now since because it is read in a different way, this has to be reduced as VDD minus VOV2. So I have just put this modulus across this VOV2 for this transistor. Yeah, PMOS will have VOV as a negative value, okay? But for an NMOS, the VOV value will be always positive, okay? So that's the reason why I've just used this modulus for this particular thing. Any doubt in this? Yeah. Now, what was our previous problem that we had before? In the case of a common source amplifier with diode connected, yeah. What was my VO max in that case? It was equal to VDD minus VTH. Now, this time, what has happened to our VO max? It is VDD minus VOV. Now, which one is good? Diode connected, say for example, you have 0.7 as your threshold voltage for your technology. Then I'm reducing the topmost value by an amount of 0.7, right? Whereas in the case of VOV, the VOV can be fixed around 0.1 to 0.2. You have a control on it, okay? So based on the value of VB, I can have a value of VOV in general, I think 150 millivolt to around 250 millivolt is the range that they use it, okay? So in that case, the VOV value is pretty small compared to the 700 millivolts, am I right? So in this case, I have a bit of more headroom than compared to my CS amplifier with diode connected load. Is that clear? So it's a kind of advantage for us, right? Yeah. Now, I think I've given enough base. So now let us go for calculating the small signal gain. So by the time I'll just copy the circuit, you can just bring out my answer so that, or I will do it again. So what is the small signal gain for the circuit? You should be right now in a position to quickly tell. And this is my M1 and M2. So what is this gain? Gain is always the product of GM times R out, right? So what is the GM of the circuit? So while computing this capital GM, what I do is that I try to short this particular node to the ground. So in that case, whatever the resistance that it poses will not be counted in, taken into account. Okay, so the only thing is that I'll be concerned with this input to the output, and what is the transconductance between them? What is the current that I will be drawing in this case? It is the ID1 itself, right? What is the ID1? It is GM minus GM times that of V in. So if you, I think all these things we have done already. Nothing new I'm talking. So in general, the capital GM of this particular circuit is nothing but it's minus GM1 itself. There is no change. Okay, almost all the circuits that we have discussed, the capital GM stays the same whenever I talk about a CS amplifier, which is a simple structure. Clear? Now, what about the R out? So how do I find the R out? No, when I look upward, I'm looking into the source or drain. Yeah, whenever I'm looking into the drain, what would be the output impedance? Why 1 by GM dash is coming? It is just R naught, right? RO2, right? So whatever I look here is I'm looking into RO2. The same way when I look down, what is the impedance that I'm seeing? Yeah, RO1, just because I'm looking into the drain again. Okay? So both these resistances are appearing in parallel, and due to which I can write this as something like RO1 in parallel with RO2. That's it. It's as simple as that. Is there any fishy about this expression? You have to recollect what I have discussed before, and then you need to come up with a question. In case if you are not questioning me, I will just tell this is the answer and then I will go for it. Okay? This is the answer. There is no doubt in it. But it has to somewhere pinch your mind. In case if you are not questioning that pinching, it's not job of mine. I'll just go ahead. This is the answer. I can just go ahead. I will not discuss further. Yeah. Yes. You see, the problem that we had for a resistive load was that the gain was proportional to the GM, and this guy was in turn was dependent on our Q point. So there is a direct dependency on the Q point, and that was our major drawback with the resistive load. But right now, I have the same similar expression, but how this expression is still worth in considering as a superior circuit than compared to a resistive load circuit? Huh? Q point would be adjusted, or the other way to think around is that this GM could be expressed in terms of ID, right, or in terms of VOVs. So that is the first point that I need to tell. And the second point is that who is defining this ID, the Q point in this entire circuitry? M1 or M2? M2, right? So in that case, I cannot use this VOV concept of my M1, okay, because the point is that the M2 is not defining the Q point at the output. It is not defining my V out Q. It is not doing so. But what it does is that it defines my IDQ. It only defines that. It never defines the V out Q. So in order to define this V out Q, what we did is that we used an extra circuitry which we called it as common mode feedback, and that helped us to define the V out Q. But otherwise, the circuit by itself doesn't provide me the V out Q. But what it does is that it provides me the IDQ. So in that case, I have to go for a GM expression that purely defined by my IDQ. Okay, so this IDQ is fixed by my M2 transistor, and due to which the GM will not change. Okay, until otherwise I vary my IDQ itself through my M2 transistor. The variation in this DC will not affect my Q point of my GM. Is that making sense for you? Yeah, you have to somehow connect it because it has not been explained in any of the textbooks. It is from what I believe that it is correct. I'm just teaching you here. In case if you have some sort of contradictory or if it is not convincing you, then we can have a kind of discussion on it. But this is what I believe, and this is how it happens, is what I think. Okay? Yes, no, or in between. If you are in between, you have to question me. Otherwise, I cannot go ahead. So the only thing is that I still have the same thing, that the gain is proportional to the GM, but the GM Q point that I have inside this is not defined by this M1. It is defined by this M2 through IDQ. Okay, so I have to use the GM, which is defined as a square root of 2 ID kn dash W by L. I cannot use the other forms here, okay, to define my GM onto this expression. That's the only thing. I believe that is correct. Okay, yeah. So having done this, what we do is that we'll just quickly switch to the last type of common source amplifier. With Triode. Okay. So basically this circuit is just included just for the completeness, and nobody uses this kind of load for the circuit. So in order to talk about this, since because it's not a circuitry that has been extensively used, what I do is that I'll just go with an input device which is a PMOS. Okay. So let me take this one as my M1, and in the place of a load, I'll just use an NMOS structure. Now, is this structure the same as that of my CS amplifier with a current source load? Yes. The only thing is that I've swapped my M1 and M2 with PMOS and NMOS. That's it. Okay. So otherwise, this is the same structure that we had before, and the only difference that about to come here is that the value of VB. Because this M2 has to be operated in the triode region. Now, how would we do that? How will I ensure that I am in the triode region? So let me plot this ID versus VDS graph. Okay, so the reason why I just choose this load as an NMOS is just because I can plot it easily. Okay, so I'll just use this ID versus VDS. Okay. Now, any value of VB that I've chosen, okay, there are possibilities that I can enter into any of these segments, right? But I just want to make sure that my transistor has to be operated only in this particular region and not in this region where my transistor gets into saturation. I don't want to enter. So what am I supposed to do? Yeah? Yeah, I have to work with my VDS. So I somehow have to make my VDS 2 to be less than VOV, right? So this value that I have is a point that separates the linear from the saturation regime, and the point that separates is nothing but my VOV of second transistor, or the VOV2. Now I have to ensure that the VDS2 is supposed to be smaller than this particular value. So now how will I do that? Who is fixing my Vout Q? Huh? V in 1? Oh, sorry, M1 or M2? What I said, for a common source amplifier with a current source load, who was fixing our Q point? Huh? External circuitry. Here again the same thing, right? Nobody else is there to control this because I'm connecting both the drains. The drain cannot control that particular quantity. Okay, so I need an extra circuitry again in order to make the circuit to operate. So I need a common mode feedback kind of circuit which will help me to define the Q point or the VDS value such that the value of this VDS is always smaller than this VOV2. Okay, otherwise it is not at all possible. Okay, so we need an extra circuitry as we had before for a common source amplifier with a current source load. So there is one drawback. The second drawback is that let us assume that we have somehow achieved that my transistor M2 is operated in the linear regime. Now what is the small signal resistance that imposes for us? Is it equal to R0? R0 is a kind of output impedance that I have when I look through the drain of a transistor when the transistor is operated in saturation regime. But can I still use the same thing? No, it is not possible. So what I do is that I will use this formula that I used for computing the R0, okay, or R out or something like that. Okay, so this is for the linear region, and what is the derivative that I have to use in order to compute it? Dou, okay. I think 1 upon R naught I will write it. So it is dou ID by dou VDS. This is the formula that I have to use, right? So now in this case, what current I have to use? Linear region current. So I'll just use this Kn dash W by L VGS minus VT into VDS. Okay, yeah. So this has to be made a derivative. Okay. Now I also consider that the value of VDS is so small. So in that case, what I can replace this, or I can neglect this particular VDS square. Okay. So let us assume that my VDS value is smaller than the value of 1. Okay, much smaller than that. So in that case, I can neglect this particular quantity. And now that I just want to make a derivative of it. So what is my R on? I will make it as R on just to distinguish R on as a linear resistance and R naught as a saturation resistance. Okay. Okay. So R on is nothing but Kn dash W by L VGS minus VT, and that is the small signal resistance that I have in the linear region, right? Now let us talk about the drawback of this. One of the major drawbacks that we had faced before is this common mode feedback. We have to use a common mode feedback to ensure that my M2 is operated in the linear region. Okay, and the second drawback that we have is that this R on is dependent on the process parameter like the Kn dash. Okay, so when you see the mobility, threshold voltage, all of these parameters in general varies with respect to the temperature. Also within the wafer itself it has variations. Okay, so I cannot precisely control those values. Say for example, through this R on I need a resistance value of, say for example, 20K. Okay, this 20K is very difficult to control just because over this entire die the Kn dash parameter will vary. So there is no control for me to define an appropriate value of R on in the circuitry. Does that make sense? R on depends on the process parameter. Because of this dependency, fixing R on to a particular value is a bit harder. Okay, is there any other drawback that we can think of it? What about the swing that I can have? What is the base value that I have for this output? Is it in the middle between VDD and ground? What we did is that in order to make this M2 to get into linear region, the Q point of this device has to be has to ensure that my M2 is in linear region. So what I do is that I just put my Q point here. So this Q point is almost close to the value of 0, right? And over this I have to have my swing. Okay, I cannot have, I can have go around to the top, but when I come down I be clipped off. Okay, so the swing around that Q point is also very small. So these are some of the difficulties that we have in the case of a triode load, and I believe that nobody uses this kind of load for a common source amplifier. Okay, so we'll just talk about the second category of our common source amplifier, which is called as CS amplifier with source degeneration. Okay. Now we'll just quickly begin talking about this gain. Now what is a gain? Again, it's nothing but the product of GM into R out, and I need the answer for both the capital GM and the R out. I think we have already done this, right? Yeah, I gave a hint, something like this, right? So it would be like minus GM1 into R naught 1, and then at the bottom we could able to write as simple as Rx. Now what is Rx? Is nothing but the impedance that I see from the bottom, okay, from the drain of my M1 transistor. What is that impedance? Okay, R naught. That's it. Yeah, so this is more important, GM R naught RS, because whenever I look through the drain, the source resistance will be amplified by the intrinsic gain, okay? And if I include even the body effect, then it becomes as GM prime, okay? And this value is nothing but my Rx value. So if you could able to recollect this, it would be much easier for you, okay? So again, I have this R0 and Rx, the resistance are getting nullified. So the leftover term is just the Siemens, and what we wanted as a capital GM is also a Siemens, okay? So the units are getting proper here, clear? Yeah. Now what about this R out? Yeah, so when I look up, what I have is RD, and that goes in parallel with Rx itself, right? So the total gain, I can write it as AV into minus GM1 RO1 divided by Rx, and this quantity I can write it as Rx RD divided by Rx plus RD, okay? Now there are some common terms which we can cancel out, sorry. So that would end up having a result which is GM1 RO1 RD divided by Rx plus RD. Okay. You see, we are not worried about how we are getting this formulae, okay? But you have to use a smart way to think back and then get this answer. You cannot go around and then do the small signal analysis and get the gain expression for this kind of circuitry, because we will be asking for 1 mark, and for 1 mark, don't do the small signal model and then get around the answer. You should be in a position to smartly get this answer. Yeah, so now that we have got this expression, let us have a deep look into this. So in case if I assume that the lambda is equal to 0 and this gamma that is equal to 0, now how does this expression steps down? If you want, I can get back this. We'll work with GM itself. What happens to the GM, which was defined as something like GM R0 and the whole of this, right? So GM1 divided by, I just divide this entire thing, so I'll have something like RS R0 and then GM prime, I think RS, yeah, something like this, right? Yeah. So what happens to this expression when I have this both lambda and gamma that is equal to 0? So what would happen to this expression? What happens with this term? That becomes 0 just because we are having a quantity divided by an infinity, so this goes to 0. And what is left over is just this formula, which is GM1 divided by 1 plus GM1 times that of RS, right? So I'm just going to rewrite this entire formula into something which is manageable. So, okay. Now let us look across our R out. So R out was defined as RD in parallel with the Rx, which is again R0, RS, GM, R0, RS, right? So what happens to this quantity? Yeah, so this particular part, what happens to that? Infinite, right? Because R0 becomes infinite in that case. So I have something infinite in parallel with RD. So what happens to this effective value? Yeah, it is just RD. Okay. So now, based on this, I can write this gain to be just a product of RD divided by 1 by GM1 plus RS with a negative sign. Now, let us have a look into our circuit. So, I think it gets hanged up. Yeah. So whole of this formulas has gone off. I'll just make a quick. Yeah. So now what I'm going to do is that in the case when I have lambda and gamma that is equal to 0, what is the impedance that I'm seeing across the source? It is just 1 by GM, because R0 will not be there just because lambda is taken as 0. Okay. Yeah. So in that case, I have this 1 by GM1, and there is a resistance here. So I have two resistances in, right? So effectively, what I'm seeing here is that there is a summation of 1 by GM1 plus RS. So this entire resistance is nothing but my source resistance, right? What about this RD? When I look up, drain resistance, and when I look down, I'm looking at an infinity. So they both in parallel. So what I have here is nothing but my drain resistance, whereas at the bottom what I have is a source resistance. Okay, so one could even apply the same concept even for this circuit. Okay, assume lambda equal to 0. What is the gain of this circuitry? Minus GM1 into RD. So how I can rewrite this? RD divided by 1 upon GM1. So what is this RD? It's nothing but the drain resistance. But where is this 1 by GM coming from? Looking into the source terminal. So when I look through the source terminal, just because lambda equal to 0, it is just 1 by GM. Okay, so I could still write it as drain resistance divided by the source resistance. That is all making sense? Any doubt? So you can apply for all other circuits that we have discussed. So with this, I'll just stop the session.